Okay, everyone, we have getting information from a graph of a function. In the last section, I emphasized to you that you really need to know those graphs when you look at them, be able to recognize them. So I hope that you spent some time looking at them. And if you have not, you need to do that in the near future. So we're going to get some more information from these graphs today. We're going to look at the values or the domains and the ranges, where they increase, where they decrease, and their local maximum and minimum values of functions. So you have many properties of a function are more easily obtained from the graphs than from the rule that describes them. So in other words, it's easier to get information when you look at the picture instead of just the equation. So we're going to see in this function how a graph tells us whether the values of a function are increasing or decreasing, and where we have maximum and minimum values. A complete graph of a function contains all the information about a function because the graph tells us which input values correspond to what output values. So we're going to analyze the graph of the function, but we have to keep in mind that the height of the graph is the value of the function. We can also read off values of a function from the graph. Here we have a function t graphed in figure 1 that gives the temperature between noon and 6 o'clock at a certain weather station. You will see in this graph, I want to point out here that you can see where my low values are in this area of the temperature function, and here are the Fahrenheit values. So if I want to find where is the temperature at 1, where is the temperature at 3, where's the temperature at 5, which is larger, 2 or 4, find the values where the temperature is about 25 or greater than 25. We can use the graph for all of these things. So if we take a look at 1 o'clock, the temperature at 1 p.m. is represented by the height of the graph above the x-axis at 1. So back when I take a look at that value, and hopefully you printed these PowerPoints out, or you have it in front of you where you can go back and take a look, you can see at 1, it's about 25. And similarly at 3, it's about 30. And at 5, it's about 20. So since the graph is higher at x equals 2 than it is at x equals 4, it follows that the value at 2, the y value at 2, is going to be larger than the value at 4. So the height of the graph is 25 when x equals 1 and when x equals 4. So in other words, the temperature is 25 at 1 o'clock and 4 o'clock. The graph is higher than 25 between 1 and 4. So in other words, the temperature was 25 or greater between 1 p.m. and 4 p.m. I don't know about you, but these temperatures start to remind me of winter, and I'm not ready for that. The graph of a function helps us to picture the domain and the range. Now, the domain are your input values. So those are your x values. Sometimes we'll call it t for time, and we might call it other things, but generally it is whatever is here on your horizontal axis, because this is your input. This is your independent variable. And then the y values depend on your x values. So these are your dependent values, and they are your range. So my range starts here and goes to this high, no higher than that. So that's my range. And my domain begins here and it goes over to here because I have solid dots on each end. So that means it starts here and it ends here because of the solid dots. So my domain is here, my range is here. Now I can use a graphing calculator to draw the graph of f of x equals the square root of 4 minus x squared. Notice we're just looking at the positive square root of 4 minus x squared. So let's find the domain. So here is the graph. When I take a look at this square root of 4 minus x squared, I can say my domain will go from -2, including -2, to 2, including 2. That's why I have these closed circles right here. So my domain is this. Now where is my range? So my range are my y values. So I take a look at my y values, and my lowest y value is 0, and it travels up to the highest value that I have for this section, and that would be 2, and including 2, because there is a value there. So this is my range, and this is my domain. Now let's take a look at where the graphs are increasing and decreasing. What you have to realize is when we're looking at increasing and decreasing, we are actually reading the graph from left to right. Okay, so we're reading the graph beginning here, like we're walking on a walk, and we are going from left to right. Okay. Hence one of the reasons why we have this arrow here and why they're getting away from the practice of putting it on the other end. Because when you read the graphs, you read them from left to right. So if I were walking along this graph, and I'm walking along this graph, I start here and I'm climbing. I'm climbing, climbing, climbing. I'm going up a hill. That means I'm increasing. When I get to this moment where it changes from increasing to decreasing, that is going to be important when we start looking at calculus. The moment where we change from increasing to decreasing. Now I'm going to go down the hill. So I'm decreasing, decreasing, decreasing. I get to another moment where it changes from decreasing back to increasing. So now it's increasing. So they're emphasizing this because you will need to understand this in calculus. It'll give you a lot of information about your calculus equations, when prices may go up, when temperature goes up, when heart rates may go up, when medication in the bloodstream might be more or less. So those are the reasons that we're looking at the increasing and decreasing. So again, you're looking at increasing, again, if you go from left to right. So I'm here and I'm going in this direction. And if I'm walking along this, I'm going up, then it's increasing. If I'm walking along this, again, from left to right, and I'm going down, it is decreasing. So let's sketch this graph. I see that it has the degree of 4, so it's going to be of x to the 4th value. We're going to find the domain, we're going to find the range, and we're going to find the intervals where it increases and decreases. Now, you should have a little bit of picture in your mind of what this may look like because it's an x to the 4th degree. But we also have all of these things over here that will cause it to react in a certain way. So let's take a look. Here's the graph. Now notice this negative in front of our 4th root. That's why this is actually, the ends are going down. You know, before we said if we had a quadratic or a 4th root, it might look something like this. But the negative that is right here in front of the 3x to the 4th causes this to flip over and go down. And we'll look at that later. That's actually a whole section in itself. But I just wanted to point that out to you in case you were wondering why that's the case. And then you can see all this movement that happens here in the middle. That's because we have that x cubed going on, which causes us to change some directions here. Now, if I were to take a look at this and I wanted to know where my domain and range were. Let's see what we would get. Well, my domain, it looks like it continues on here for a long period of time. So I don't know if at first, how long it continues, what it's going to do, but it looks to me like this is going to go on forever and ever and ever. And it might not go this direction quickly, but I don't see it ending anytime soon. So I would say that my domain is going to be from negative infinity to positive infinity, because I could go way out here. I'm going to go really far down, but I'm going to find a value. Now, as far as my range, it looks like it goes down a long way. So from negative infinity this way. But then I do have this top value right here. That top value, 1, 2, 3, looks like, unless this is, oh, this is 40s, going in 40s. So 10, 20, 30, 40. So this is 30 would be the highest range value that I get. Let's see what they figured out. Okay, so again, because it is a polynomial, they're saying polynomial right away gives it away that it's all real numbers for the domain from negative infinity to positive infinity, which is what we said. Now, we said about 30 was going to be the high value. They suggest you use the trace feature on your calculator. And if you are using a calculator for this, you would use the trace feature. And you're going to go up to that high spot and see that the highest value is 32. So we did pretty good when we estimated by looking at it, saying it was around 30. It is 32. And again, you can use your trace function on your calculator, and that'll help you get that value. So we'll see that f is going to be increasing from negative infinity to negative 1 and from 0 to 2. And it's decreasing, going down from negative 1 to 0 and from 2 to infinity. And again, I suggest you go back and look at the graph and make sure you understand as you're going from left to right, make sure you remember that you're going from left to right when you're reading this. You're going to go up from negative infinity to negative 1 and from 0 to 2, and then you're going to go down from negative 1 to 0 and 2 to infinity. Local maximum and minimum. Now, if I say to you, what local person is famous in your community? You're thinking of the area right around where you live. And this is the same concept when we're looking at local maximum and local minimum. What right around that area is the highest point? What right around that area is the lowest point? And they remind you that finding the largest and smallest values is important for many applications, and it certainly is. You might have a highest cost, highest price, highest amount of medication in the bloodstream, or the lowest amount also. So if a function represents revenue or profit, then we're interested in a maximum value. If we're looking at cost, we're interested in a minimum value, minimum cost. We want the minimum cost to be able to produce something. And we can find these by looking for local maximum and minimums if we have the formulas. So here we have around this area, what is the highest value? We would call that a local max. Around this area, what is the smallest value? Call that a local minimum. Around this area, what's the highest value? That will be your local max. And around this area, what is the lowest value? Would be your local minimum. So right around you, you're looking at here, what's the highest point? And that's all these say, is that you're going to have this value where nothing else is bigger than you, then it's a local max. If you have this value where nothing else is smaller than you right around you, then it's a local minimum. Now we can find local maximum and minimums, again, using the graphing calculator. You can trace it to come up here and you're going to trace along these sections and find out where I have my highest value and where all of a sudden now these values are not the highest. So you can find your local maximum here and you can find your local minimum here by tracing and looking at your values. And again, this slide is reminding you that you're going to have that value that's bigger than everything else that's close around that area. Let's find the local maximum and minimum values of this. Now, in your mind, think about it. What is this going to look like? Looks to me like it's a cubic. I don't see any x squareds or x to the fourth in there. The highest degree is 3. So let's take a look at what this graph looks like. Here it is. Notice it starts down here, just like cubics do. It's coming up. Now, I'll remind you of what our parent function looks like. It comes up this way, and it goes like this, and it comes up this way. So it starts at the bottom, and then it goes clear up to the top. And this is similar. Maybe I shouldn't use red because I don't want to confuse it with this one. So the minus 8x in the middle is what causes the difference in between here. So there appears to be one local maximum between -2 and -1 and one local minimum between 1 and 2. And again, you want to go back and look at your the last slide so that you can see that well. So if we want to find the coordinates of the local maximum point first, what we would do is we would focus in on this area right here. Enlarge it so we could be close to the point. And we would use the trace function to find this point right here where nothing is higher than the point, and that will give you your max. So we use the trace function again, and we find the local maximum value is 9.709. And that occurs, and again, it'll give you this in the calculator, it'll give you where it occurs at -1.633. And that's using the trace feature. And we would do the minimum in a similar fashion. So here's the minimum. I want to focus in on this area right here. I'm going to use the trace. I'm going to get as close as I possibly can, and it'll tell you that at about -7.709, right about here, and that happens at 1.633, and that's using your trace function on your graphing calculator. Okay, well, we learned a little more about graphs and how we read them. Increasing and decreasing our local max, our local minimums, and we'll be getting ready to go on to the next section. So I will talk with you soon.